Good morning, everyone. So, today for the mini course, we have Christoph Schweigert from Hamburg, and he will tell us about modern categories of the tensor categories, some structures, and some applications.
Yeah, thank you very much to the organizers for putting together this very nice workshop. I've been to a couple of workshops in my life. This is one of the nice ones. Thank you. Some of you, or many of us these days are attending talks, you have a tablet. So if you want to have the slides on your tablet to take notes, or then you can download it at this address. So I'm not responsible for this part of the address. So it's https://uni-hamburg.de/home/my name/sky with a capital S. Okay, so I want to review quite a couple of things we have been thinking about. So many people are involved. If I give more priority when I give names to collaborators, in particular junior collaborator, I apologize in advance for the distortion of the, if there's a distorted impression of the subject. Of course, many other people have contributed here as well. Okay, so the talk will have two parts. There will be a first part, which will be rather putting the theoretical foundations. And then there will be a second part where I want to apply the structures we developed in the first part to do constructions that are important in mathematical physics and that are of interest to practitioners. Of course, practitioners could use structures before they understand it. But on the other hand, this is a chance to discover interesting structure. Cool. So I should define the setting. The setting are finite tensor categories and finite module categories. And we've seen a lot of this in this, there's a small delay between my iPad and the slides. We've seen a lot of this in earlier talks, but still let me quickly go through this. So I'm always working over a field, and the structures are interesting and relevant already if you take as the field the complex numbers. I'm working with categories which have finiteness properties. This will ensure the existence of certain things, and the categories I have in mind are linear abelian categories. And if I talk about finiteness properties, then a finite category will be a category that is equivalent, a linear abelian category that is equivalent to finite dimensional modules over some finite dimensional algebra. And of course, you can also characterize this intrinsically. So it is a category with finite spaces of morphisms, vector spaces of morphisms. Objects have finite lengths into decomposition series, enough projectives, and there are only finitely many isomorphism classes of symbols. There is some interest to push the results beyond this framework. Part of the results have pushed beyond this framework. I will not go beyond this setting in this talk. What I should mention is an underlying topic. We did on these slides this characterization in terms of an algebra, because different algebras can be used to describe one and the same category. These are Morita equivalent algebras. So algebras will be kind of a coordinate for categories, and we will encounter this topic at a different level in a moment. Then we will be interested in monoidal categories. And a finite tensor category is a monoidal linear category that is finite in the sense I just explained. And then it has moreover the property of being rigid. And I will briefly review rigid on the next slide. You can see rigid as a finiteness property, but rigid is a very strong property. And I should say that in applications, there is a need to go beyond rigidity, but everything in this talk will be in a rigid setting. What goes beyond rigidity is for a talk next week by Simon Wood. just to fix terminology and make contact, fusion categories are, so those categories, if they are semi-simple, we will not impose semi-simplicity in the first part of the talk, although in applications one frequently goes to the semi-simple case. Now, concerning rigidity, if you have a monoidal category, then you can ask whether objects have a right dual. So what is a right dual? That's another object which comes with some evaluations. So you have a morphism from the monoidal unit to a tensor A dual. There is a graphical calculus which I will not frequently use, but I'm using it here to explain the notion. It comes with an evaluation, which is a morphism from A dual to A into the monoidal unit, and they obey zigzag relations. So these are two relations. So if you look at the composition of evaluation and co-evaluation, then this is equal to the identity on the object A. And similarly, there's a second zigzag relation. And a monoidal category is right rigid if every object has a rigid dual, and it is rigid if every object has a left and a right dual. That's what we will impose. We will not impose that left dual and right dual are equal, and imposing that two objects are equal is not a good requirement, but we will consider such type of requirements or alternatively conditions on the double dual. So, examples, if you take the category of finite dimensional modules or finite dimensional Hodge algebra, then this would be such a finite tensor category, but important examples are not of this type. Then this rigidity has rather important consequences. So it implies in particular that the tensor product on a rigid category is exact. And we have internal homes. So let me briefly look at these internal homes, just let me see it. Here we have the tensor product, and we now can prove in this setting that the functor tensoring with W has a right adjoint. And this right adjoint is the internal home, the inner home. And the inner home gives us a functor, in this case, from home, sorry, that should go to the pencil. So it gives a functor from C pop, C to C. And since the tensor product is exact, it has also a left adjoint, which we call the cohom. That's the name that's in the literature. So that will play the part. Now let's go to a structure we have seen in past talk on Monday, module categories. So a left module over a monoidal category. It is a linear category. We will require it immediately to be a finite category. And it behaves to a monoidal category in the same way as a module behaves to a ring. So think about a monoidal category as the analog, as the categorified version of the ring. That is the categorified version of a module. So there is a functor, and there should be an axiom for an action, but we never ask for equality. We introduce isomorphisms. And these isomorphisms have to obey coherence conditions. Then this is a pentagon, and for the unit constraint, it is a triangle axiom. You can define left modules and right module categories. You can define a bimodule category, and you should be aware that this requires one more piece of datum, which implements the left action from unit. So that's also a piece of structure. And then you can define module functors and module natural transformations, and they are defined in the obvious way. Now, we call a module category finite if the underlying category is finite, and you require that the action is exact, is linear in each variable, and right exact in the first variable. That's enough to require. Anything else follows by using rigidity. The notion of a module category is a rather old one. It dates back to the 70s, somewhere. You can introduce it formally, but my point in this talk is to explain why they are interested in what you can do with them. Yeah, so the notion in itself is not a big deal. Okay, examples. Well, if you have a finite dimensional Hopf algebra, then if you consider H mod, then the category of finite dimensional vector spaces is always a finite module category over H mod. No forgetful functor gives you such a structure. Well, then more generally, if you fix a co-module algebra for a Hopf algebra H, then H mod is an H module category just by using pullback. And one way to get examples is the following. Suppose in your monoid category A, you have an associative monoid, so that's an object and a morphism from A tensor A that obeys associativity. Then you can consider the category of right modules. And if you're given a right module, it will stay a right module in an obvious way if you tensor it from the left with any object in A that defines the left action of A. So right algebra modules are left module categories. And yeah, then there's an example we've also seen in Matti's talk. So if you take for G-graded vector spaces, then you can fix subgroups, and then you take the object which consists of the simple objects in the degrees that are given by the subgroup. And now let's suppose you can twist actually the associativity on vector G. Let's suppose we do not do this. Then you can define a multiplication on this object A given a two-pole cycle here, and that gives an associative multiplication. And one can classify such module categories, and this classification result is a very classical result of Victor Ostrich. There is another situation where you can classify. If you look at fusion categories associated to SL2, this is like the category of finite dimensional modules over the Lie algebra SU2, but truncated at a given moment, then and with some different tensor product, to be honest. But experts know what I'm saying. You can classify this, and this leads to an ADE classification. This was something which has repeatedly in the history of conformal field theory got people very excited, but it's a phenomenon due to SL2 and the specific structure of Frobenius Perron dimensions in this case. In general, you should keep in mind that this example of taking subgroups is quite characteristic. Classifying subgroups of a group is not an easy problem, and classifying module categories is not an easy problem, and we are not going to talk about this. And by the way, in some other communities, module categories are called quantum subgroups. Whether you want to call them this way or not, doesn't matter. Okay, so if it's not possible to classify them, and you see the example of taking vect as the monoidal category and taking any finite dimensional algebra in vect shows there are far too many module categories to have a nice theory. You have to find a nice class. So this is really important here. What we do is we use the notion of an exact module category. So an exact module category over a finite tensor category is a module category such that if you are acting with a projective in your monoidal category P on any object M, then you obtain an object that is projected in the module category. This doesn't explain the word exact, and it's maybe not directly obvious that why this is a useful requirement. So let's discuss this a bit. What we can already say is we do not have to impose exact the same condition which are requiring projectivity here for M, because that's automatic. Okay, so the first thing is exact module categories exist. If you take a monoid category, it is a module category over itself in the same way as any ring is module over itself, the left regular module. And this is an exact module category for a finite tensor category. Rigidity is important. Then module functors out of an exact module categories are automatically exact. It's a very strong property, and that explains the word exact. And there was something on the slides of Matti, which he unfortunately didn't have enough time to discuss in much detail, but the question whether in which case, given an associative algebra A, the module category given by right A modules is exact has been an open question for quite some time, and there has been important progress recently. And yeah, then next thing I should point out for exact module categories is also for exact module categories, you can define internal homes and cohomes. So the internal home is defined by considering this and looking for, again, an adjoint. And you see that here in this situation, let me just note this here on the transparency, the internal home is an object in the monoid category. So the internal home for a module category takes M off and gives us an object in the monoid category A. And for an exact module category, this is an exact functor. So the home obviously is not necessarily exact, because an exact module category over a finite tensor category that is not semi-simple is not necessarily exact, but the inner home is exact. So we will see that it is, in my opinion, quite appropriate to think about exact module categories as module categories which are relatively semi-simple, so semi-simple relative to the monoid category. Good. Now, let's see what you can do with such an exact module category. It's kind of, the setting which is helpful to consider are Morita contexts. I've briefly mentioned Morita theory for algebras. You can do a categorical Morita theory. So what's this? You have a monoid category. Maybe I want to delete this. So you have a monoid category, you have another monoid category, and you have a bimodule, which is an A-B bimodule and an B-A bimodule, and they fit together into a bi-category with two objects, and this summarizes the structures of these module categories. The Morita contexts we are interested in, which are sometimes called strong Morita contexts, they have the additional condition that the bimodules are invertible in the following sense. If you would have ordinary bimodules, then we would take the tensor product over the algebra. There's something like this for categories. How do you define the tensor product over an algebra? Well, you look at balanced bilinear maps, and then you're looking for something which has a universal property. Here you're doing the same. You introduce the notion of a balanced functor, and actually you're doing this for balanced right exact functors, and then you can show that in this setting there exists a category which has the appropriate universal property. That's the relative linear product. And that defines for you categorical Morita contexts. It is a fact that quite a few constructions in mathematical physics are expected to be invariant under change of the Morita case. So we want to understand this. And okay, there's a first result. If you have an exact module category, well, then it's a module category over a monoidal category, but we have very quickly, we have another monoidal category, which is frequently called AM star. Well, you take here, in this case, you take module functors, A module functors from M to M. We've learned that for an exact module functor, they are automatically exact. Exact module category, they are automatically exact. So I don't have to tell you right exact or left exact functors. They are automatically strong module functors. So this is again known and shown to be a finite tensor category. And we need another bimodule. And you can show that this category here of module functors into A does the job. And you get a strong Morita context, and you can even show that strong Morita contexts are of this form. So if you think of algebras as coordinates to describe some linear category, we want to think of monoidal categories also as kind of coordinates, which we want to change in constructions. This will be made very explicit in one example. Then these Morita contexts are important, and we know that they actually come from exact module categories.
Christoph?
Yeah.
Do you assume that M is indecomposable?
Yes, sorry, I should have. Yeah. Thanks. So there's a notion of indecomposability. You can show that every exact module category can be written as a direct sum of indecomposable ones. And I should have added here the qualifier that this is indecomposable. Thank you. So just a brief word. Morita equivalent algebras have the same center. There's something similar here. So that's the Trinfeld center. Well, how can we briefly explain the idea? You define the center of an algebra in a way which everybody has seen. This is an equality. If we now define the center of a monoidal category, then we would say that these two objects have to be equal, but objects in the category are never equal. So there should be an isomorphism instead, which obeys suitable coherence constraints. Such an isomorphism is what is called a half-grading. You ensure by the hexagon type axiom that this is compatible with, this gives a compatible grading. And indeed, the category which is defined on these objects, together with the appropriate morphisms, is a braided monoidal category. And it turns out that two finite tensor categories are Morita equivalent if and only if the Trinfeld centers are braided equivalent. So the easier direction is to show that if they are Morita equivalent, and then the Trinfeld centers are braided equivalent, but the converse holds. These are depending on how you formulate it, old or relatively recent results. Good. There's a last thing we have to look at. You've seen these Morita contexts have been bicategories, very simple two-object bicategories. Now, in a bicategory, we have the notion of a dual or adjoint. So the adjoint to a one morphism in a bicategory is a one morphism. If this goes from X to Y, this goes in the other direction. And two morphisms which exhibit the adjunction, they obey the appropriate snake relations. I think everybody here has seen adjunctions. And having a dual is a property. Well, what you can check by a calculation is that if you consider this bicategory that's given by an exact module category, this bicategory has duals. And the duals here, well, they are living in some different one morphism. So if I take the dual of something in the module category M, remember we had M going this way, but we have in the other direction M bar, which was a functor, a module functor from M to A. Then you compute and you see that the dual, almost by definition, actually, is the right dual is the home and the left dual is the co-home. Good. So this was laying the very basic ground. And I now want to put more structure on it. I want to put on this pivotal structure. Actually, let me explain what a pivotal structure is and what let me motivate it. So a pivotal structure on a rigid category is a trivialization of the bidual. So finite dimensional vector spaces famously have this. Infinite dimensional vector spaces don't have this. So now here you see that it is a monoidal isomorphism from the identity to the double dual. So what is important about it? You can verify that it's not only identifying an object in its double dual, but it's also identifying left dual and right dual. Actually, there are strictification results for this. And another property that is quite important and that you should keep in mind is the following one. Suppose we are considering a morphism from A1, A2 to AN into the monoidal unit. I'm always reading morphisms from below. Then you can do the following thing. You can map it to a morphism where you use the duality, and you don't do anything else. Now, if you keep track, you're inserting dualities here. And if I would do it in this way, I would end here on the double right dual, but of A1, but I have an isomorphism from the double dual to the original object. So I have a natural operation, which gives me a morphism here. And it's a pleasant exercise to check that if you're doing this n times, you're getting a morphism again from A1 to AN, and it is the same morphism. So put differently, these form spaces have a cyclic invariance. And we've yesterday seen graphs decorated where the vertices you had some cyclic property and they were decorated by other things, and we will do something reasonably similar in a moment. Okay, not in a moment, in the second part of the talk. Sorry. Yeah. Okay. Now, why do we insist in this structure? Actually, in my point of view, on the subject, there is a dichotomy. You can either work with tensor categories and algebras, or you can work with pivotal tensor categories. And if you want to build TFTs from this, in one case, you get TFTs, which are defined on frame manifolds. And in the other case, you're getting a TFT, which is defined on oriented manifolds. So in a sense, if you're in the first line, in the first line, the algebra is simpler because you have less structure. But the geometry you ultimately have is more difficult, more restrictive, and it's typically also not the geometry practitioners who are using these structures in mathematical physics or theoretical physics want to have. So if you want to work with oriented manifolds, so consider cobordism categories of oriented manifold, then on the algebraic side, you have to work with these pivotal structures, and then, for example, the notion of an algebra will be more or less implicitly replaced by the notion of a Frobenius algebra. And to do this, I want to introduce a tool. This is not the only path to the subject, but the tool is interesting in itself. So I want to explain the notion of a relative Serre factor. So if suppose that M is an A module, then we could ask a module category, I should say. If I'm saying a module, it's mostly in a module category. You could look at the ordinary home and at the co-home and ask that the co-home is isomorphic to the home. And maybe it's isomorphic up to the action of some function that's to be determined. This is not a very good idea because if you're just working in the setting I sketched, because the home is left exact, the co-home is right exact. So, the home was constructed as a right adjoint, so that the co-home is a left adjoint. So this forces the home function to be exact. You're working on semi-simple categories and you want to go beyond semi-simplicity. You know that the story goes on in certain contexts that you don't consider the Serre functor everywhere. Then you define projectives, mapping projectives to injectives, and you go into the right category and you get the interesting stuff. Here we are doing something else. We are not asking this for the ordinary home, but we are asking this for the internal home. And if you are asking this for the internal home, this requirement makes sense. And you're introducing in this way two functors, which we call relative Serre functors. Relative Serre functors because we are working with the module category in the sense relative to the monoidal category. These Serre functors exist if and only if M is an exact module category. So that confirms again this intuition that exact module categories are relatively semi-simple. Exact Serre functors are equivalences of categories. And this is now important in this story. We are working with module categories, so it's quite reasonable to what happens if I'm applying the Serre functor to A acting on something. Is it a module functor? If it would be a module functor, then I could simply pull out A. This is not true. You can pull out A, but at the price of a double dual. So it is a twisted module functor. Okay. So now, suppose we have on our monoidal category a double dual, then we can play the following game. It's very interesting to ask that the Serre functor is trivialized. Trivialized in what sense? Well, it should be isomorphic to the identity functor. Isomorphic in what way? Well, if possible, as a module functor. It is a twisted module functor, but we have a way to trivialize the double dual. So we can impose this type condition, and we can say that a pivotal structure on an exact module category is a trivialization of the Serre functor as a twisted module functor. So this commutes if we use the pivotal structure on the monoidal category to get rid of the double dual. And this is a very useful thing. And I should say, if the module category is indecomposable, in the sense we just mentioned on this question, then by a Schur's lemma type argument, the pivotal structure is linked up to a scalar. So it's not dramatically much structure. The second comment is that if you take the inner end, it is always an algebra, a monoid object in game. But if the module category is moreover pivotal, then, and this is a result of Shimizu, then this inner end has even the structure of a Frobenius algebra. So what you can do is we use the Serre functor to identify this. And I have made a typo, but here I can correct the typo. I can identify this with the dual. Then the Serre functor is trivialized. This here came from an adjunction. The adjunction has a full evaluation. So we take the dual of this co-evaluation, we have a natural morphism into one. That's a Frobenius form in the sense of providing a non-degenerate bilinear form on the algebra. So trivializing Serre functors in this, trivializing the relative Serre functor is the source of Frobenius algebras. And Frobenius algebras are very nice things if you want to construct certain things in topology and applications. So this is here. Let's put this a bit into context. So we know what duals on a bi-category are, and if we have duals, then we can act as the identity on objects. We apply on the one morphisms, we apply them in the way they are defined. And then a pivotal structure on such a bi-category with duals is again a trivialization. This is a trivialization in the following sense that the identity functor in the double dual that we should have a pseudo-natural isomorphism. And you see that something a bit unnatural happens here. If you think bi-categorically, I'm asking here that a pseudo-natural transformation has two components. It maps objects of the bi-categories to one morphisms and one morphisms to two morphisms. And we are asking that on objects, it is the identity. You can drop this, and you're getting an interesting structure, which is called quasi-pivotal structure. It is natural just precisely because of this bi-categorical point of view. We are not going to use this here, but I just wanted to point this out. Okay, now a Morita context is pivotal if called pivotal if the associated bi-category is pivotal, and you're getting now very satisfactory propositions. So, for example, if you compute the double dual of an object in M, the dual was in this category of functors. If you again apply the dual, you're back to the original module category. Is it the same object? No, it's not the same object. They are related by an endofunctor, and that's precisely the Serre functor. So the Serre functors are really also the double duals in this respect. And trivializing the Serre functor means trivializing the double duals. And the Morita context given by a pivotal module category is pivotal in this sense. So, two last facts. Well, if the first thing was I was two algebras. If two algebras are Morita equivalent, then their representation categories are equivalent. We have a similar thing here. So if we have two tensor categories, then we can look at the two categories or bi-categories of module categories, and they will be equivalent. And here, in this proposition, we see that we can add everywhere the word pivotal, and it still works out. This is important because we will use this pivotal Morita context later to change coordinates for certain systems, and it really needs to be pivotal that we can use them on systems that describe oriented topological field theories in the end. Well, and the second thing is that two pivotal categories are pivotal Morita equivalent if their centers are equivalent, but equivalent really as braided pivotal tensor categories. So this is a very nice closed theory where we can work. Okay, let's go to the last part of this theoretical part. I want to talk about Nakayama functors. Serre functors are in the classical context related to Nakayama functors. They're the derived functor of Nakayama functors. So let's study a bit Nakayama functors. And let's in particular dwell a bit on the relation between Nakayama functors and traces. And we need traces to have non-degenerate various consequences. And I will use the Nakayama functor to produce such traces. And actually, I would like to argue that the word modified, which is used, is a bad word. This is really what you should call the trace. Okay. So let me first recall a very classical result. So suppose I have two finite categories, and suppose they are given in terms of modules over two algebras, and I have a right exact functor. Then this right exact functor can be represented by tensoring with a bimodule. And this bimodule is very explicit, and I think this is basically something you should find in more textbooks. In any case, there is a similar statement that also expresses left exact functors in terms of bimodules. So we have a relation between the category of left exact functors, right exact functors, and bimodules. I don't want to use algebras, so I want to write down this Eilenberg-Watts type of functors in a basis independent way. Well, I'm not going to write them down very explicitly. I'll do it a bit more explicitly. So you have two finite tensor categories A and B. You consider left exact functors, right exact functors. And here you have your replacement for bimodules. This is the linear product, which is a product that for finite categories, it is again defined by a universal property for right exact functors. And then you have very explicit equivalences. Actually, these are adjoint equivalences. For example, let me just write down one of them. If you want to take two objects, A and B, in our bimodule category, and you want to produce a functor, this is easy. Everybody knows how to do this. We take home A, B, and if I'm writing here a tensor product, then I mean that these are linear tensor categories, which I can see as module categories over A. So this makes sense, and that's a left exact functor. So this would be the functor we find here, and I can also go into right exact functors, and the way I do it is I look at this functor, and the home spaces are by definition finite dimensional vector spaces, so taking a linear view is a completely innocent operation, and that's a right exact functor. And they have explicit inverses, which are given in terms of n's and cones. Okay. So let's accept this triangle, and let's look at this triangle in a specific case. Let's look at this in the case where B and A are equal. Of course, that's a special case. Then you know that the identity functor is a left exact functor, the identity functor in A. So I can take the identity functor, transport it here, transport it down, and I'm getting a function. However, this is not the identity functor. This is obviously a very important functor. I have a very explicit representation for this functor, and it is written here. It's defined in terms of the dual of the home and the toe end. If you do it the other way around, it will be the home and an end. There's a perfect symmetry here. And I want to explain to you that this is the classical Nakayama. So you see, these two categories here, they are monoid categories, but our transport doesn't preserve the monoid structure. The monoid unit is going to some other element and vice versa. So think about these categories as monoid categories with one more distinguished object. This is actually a dualizing object, and they have the structure of what Boyachenko and Trinfeld called cohomogeny category. we are not going to use this, but the Nakayama functor is a very natural categorical form. So still, I should take the time to convince you that this is the classical Nakayama functor, so maybe we do a small calculation better. So here are the formulae for these functors that are so very naturally given to us. And let's look at this to get to the what I call the classical case. The category is given in terms of an algebra, and I want to show to you that it can, the right exact functor can be obtained, described by tensoring with a bimodule. It is described by tensoring with one of the two canonical bimodules you have. You have A, but that's the monoidal unit, and you have A dual. Okay, so since this is right exact, the Eilenberg-Watts theorem applies, and the Eilenberg-Watts theorem is explicit. So this bimodule we are looking for is obtained by applying the Nakayama functor to our monoidal unit, to the regular bimodule. And now you see we can compute what this is, what this bimodule is. And you see this is taking the co-end of, here we have the dual of the home, and here we have A. So we have here a left module, the dual is a right module, and if it would be in the setting of, say, Lie groups or finite dimensional groups, that's a Peter-Weyl theorem. The Peter-Weyl theorem can be generalized here. This must be known in the literature, but we didn't find a reference, to be honest. And so if you know the reference, then please tell me. So the Peter-Weyl theorem is generalized in the sense that if you take the end, so the end of Y dual tensor Y, this is the regular bimodule, and if you take the co-end, this is the dual. Now, so you get the dual, and this is the functor which is obtained by tensoring with the dual. And we have this whole business of Nakayama functors in a nice conceptual framework independently of on algebras. Good. So it's also appropriate now for the Nakayama functors. You can prove that they are adjoints. If their equivalence is if the other one is an equivalence, and in this case, the category is self-injective. This sounds definitely familiar. So now the relation between this relative Serre functor, which we had here, and remember the relative Serre functor was comparing home and co-home. And the Nakayama functor is as follows. So in these finite tensor categories, there is a distinguished object which is obtained by applying the Nakayama functor to the monoidal unit. Well, this object is invertible, so there is another object such that D tensor D, D-twiddle tensor D is the monoidal unit. And this invertible object is very well known to people in algebra theory. It's the object which measures the difference between left and right indifferences. And Nakayama and Serre functor, they differ by just the action of this canonical invertible object. Other characterization of this canonical invertible object, take the projective cover of the monoidal unit and take its side. So it's also very natural, important from the homological algebra point of view. Good. So you see they are again very closely related.
The self-functor is another equivalence, right? The self-functor is another equivalence.
Yes.
And does that mean that any exact module category is self-injective?
Yes.
Okay.
Completely clear. Good. Now, just to show you that also in this Morita context, this also works out very nicely. We had this second monoid category, which was actually this was functors, modular functors from M to M. That's a monoid category. You can compute its what is its canonical invertible object, and this canonical invertible object is a composition of the Serre functor and Nakayama functor, and you can also prove that there is a distinguished a natural isomorphism from which relates acting here to the Serre functor. Now remember, the Serre functor was a double dual. Taking twice the double dual is taking a fourfold dual, and a fourfold dual that corresponds to taking the fourth power of the antipode. If you're thinking about Hopf algebras, there is a famous theorem about the fourth power of the antipode, which is due to Redford from the 60s or 70s, and this explains why we are using here this letter R, and I will call such an isomorphism a Redford isomorphism. And it can be packaged in this bicategorical setting into a trivialization, all this Redford isomorphism. Okay, now let's investigate a bit more this Nakayama functor. Remember that the Nakayama functor came from the following diagram. So I had here A and here A off. No, sorry, it's wrong. Let me write it better. So we had here left exact functors. Then we went to bimodules, and then we went to right exact functors. And here we had the identity here, the Nakayama. The identity has this property that it commutes under composition with any other functor. Now we've done quite something non-trivial on the identity, but something remains. And what is the thing that remains? Well, the thing that remains is that if I want to commute a functor with the Nakayama, and this exists for left and right exact version of the Nakayama, then you can do this at the price of having a double dual. And so, of course, the double dual has to exist, so the double left adjoint, and you have to put the right assumptions to the theorem. But what you should keep from this here is that the Nakayama comes with a lot of structure. It is a twisted module functor, and as we will see soon, and in particular, it commutes with suitably nice functors, but up to taking the double left adjoint. This looks strange, but that's exactly how things should be. So I was writing here Redford's S4 theorem. I will recover this in a moment. So this is the theorem I just mentioned. So let's look here at what this implies. So if I'm given a bimodule category, M, then I get an endo functor from which stands A to M to A acting on M. We have duals. So this is a nice endo functor. You have to compute what the duals are, the adjoints, and depending on how you set up the conventions, it so happens that if we take here the double left adjoint, we have to take in the monoid category the double right dual. But this is a matter of convention. And you see that the Nakayama functor is a twisted bimodule functor. And this you can now use to recover the Redford's S4 theorem in the sense that you are computing what this means for an object in the monoid category. And if you compare these two, then you see that these two must be equal. And that's the famous version of Redford S to the 4 that you can find in the Hamburg dictation Austin. Okay, I was promising to talk about traces. So let's do another calculation together. So take a final tensor category, and let's insist that the object P is projected. Then I want to investigate this home space. X is any object. Now, the Nakayama was defined in terms of the co-end. So this is really from A, P, and then there was a co-end here. But we insist that we work with projective objects, so the Hom functor is exact, it commutes with the co-end. We can write it in this form here, and then we can use the linearity of the Hom, and then taking a co-end, well, with something that contains a Hom, that's a useful form of the Yoneda lemma, you're getting just the other functor here. So what you're getting from just standard categorical manipulations is that this Hom space is the dual of this one. If we combine this, if we specialize this now to the case where x is equal to p, then you see in this space, Hom pp, there's a distinguished element, the identity. So the identity gives us a linear form on Hom spaces of the form NR of P. So we naturally get for any projective object such a linear form, not an endomorphisms, but an endomorphisms twisted by the Nakayama functor. I call it here the modified trace because it will be shown in a moment to have the properties of a trace. And notice that these are categories. I never said anywhere that the categories are monoidal. Yeah? And if you're teaching linear algebra, you are usually teaching this the trace before you are teaching the tensor product. So now here, well, this trace is cyclic. It is cyclic up to a twist by the Nakayama. So if I take first G and F, that has the same trace as first taking F and then G twisted by the Nakayama. And it has also a partial trace property, which is very nice, by the way. So let me quickly write it. So if I take a morphism from in the bimorphic category from A M to, so what should I do? I should apply this to NR of AM. But this is a twisted binomial functor. So this is the double right dual of N of M. So really the appropriate picture is to have here a double bidual and here M and M. And here I can take a trace even without introducing any pivotal structure on the monoid category. And if you do this, and you take this type of trace, and then you take the modified trace, this gives the same result as taking the modified trace right away. That's the partial trace property. And now, there are situations where you would like to consider not traces on twisted endomorphisms, but you would like to consider them on endomorphisms. The big problem here, it's not a problem, it's actually a nice structure in the end, is that if you want to get an endomorphism, you have two ways. You can use the explicit form of the Nakayama functor in this way, that you get a double dual here and the distinguished invertible here, or you can go down to this form. They differ by the red hot isomorphism. So I should have put here an iso. Okay, now we are assuming that we are in the case where the distinguished invertible object is trivial. So the object of interpolars is trivial. That's called a unimodular case. And in this case, we fix such an iso, and we assume that the category is pivotal, so we can trivialize. We can trivialize here. We do this in opposite directions, so that's why the choice of trivialization here doesn't matter. But it can be that this whole arrow here is a non-trivial arrow. So it makes sense to impose the condition that this is really the identity, because then we can transform those morphisms on which traces are naturally defined to endomorphisms in a unique way. And that's the definition of a spherical tensor category. So in a sense, I would summarize it by saying the pivotal structure squares to the Redford. Good. And we can again summarize this in terms of phi categories. And let me just see what else I have. Yeah, here, these are two quick remarks. So it works out all very nicely. So if you have now, if you have summarized it in terms of phi categories, you can define what a spherical module category is. And a spherical module category will have the property that a spherical exact module category will have the property that this other monoidal category is automatically spherical. And if one is a spherical module category, the other one is also spherical. And for spherical and fusion, so assuming that this is semi-simple, there is a graphical calculus on spheres. That's very well known. That's an old result from the 90s. And the two definitions of spherical, the ones I presented and the one that's used in this in the older literature, coincide precisely the semi-simple case. In the non-semi-simple case, these modified trace, which is really the good trace, this is really the appropriate thing to take. And you can show that if you have two pivotal tensor categories that are pivotal Morita equivalent, then one is spherical if and only the other one, the Morita partner, is also spherical. So this is a very nice theory. So what we have at the end of this talk is a nice theory on for spherical Morita contexts. And I think you see that we've been using quite a bit of standard algebra in a hopefully attractive setting. What I'm going to do in the next talk after a break is that I want to show you where these structures are applied. Thank you.
We have to talk to some of the about practice. I don't think you have used this. Have you actually used practice in zero way?
I doubt it. That's the honest answer. Yeah. So we didn't use Frobelius Perron dimensions, for example. We didn't use anything like the x of 1, 1, x1 of 1, 1 is trivial or things like that. But so that
you use the fact that the field is your boundary operating fluids.
Yes, we had a sure type argument. Yeah. But of course, we could go beyond this. Yeah. So it's just that the structure here is already nice. I know if you're in the simplest space, but I think it's also natural enough that it can generalize to more general situations in a natural way. So, for example, Shinizo has generalized these relative Serre functors to categories of comodules, the algebras over Frobelius, and that also works out. So, this is really nice structure. Yeah.
You did have something with the unit. Might be simple. I mean, yes, which is what we do.
Oh, yes. I think that depends on the absolutely simple. Yeah. Yeah. And it would be important in the second part of the problem. Otherwise, I wouldn't get scalar value variance. Yeah.
We have a, so you say people who want that is the
inner forms of trivial module categories are symmetric of these.
and spherical module categories are,
we don't know where they are. So, and I think symmetric, but
people doesn't mean spherical.
No, pivotal doesn't mean spherical. Spherical is a property of pivotal. Pyramid, you're invited to think of as a structure which, in the case of decomposable modular categories, decomposed by a short by argumented scalar factor, which is still a structure you should carefully take into account. Serre is a property. Serre is a property that the square of the pyramid structure is the red dot.
So it's special type of set of examples.
Yes, and it's a very interesting and valid question whether you can characterize. Martin, do you know this? Well, we can discuss this also over top of that. Yeah. No, because we had so many exciting slides that we didn't show them.
Any more questions? If not, let's begin.